Okay, so I want to talk about our 6 trigonometric functions. Now, the nice thing about these trigonometric functions is they really all have the same job. All of the trig functions, and I'm just going to use for a second here the word trig to refer to all of them. All of the trigonometric functions do the same thing. They take in an angle in either degrees or radians or really any other form of measure. The trigonometric functions take in an angle and they give back a ratio of values. Now, exactly what those values represent depend on which of the trigonometric definitions we're working with. We're working with the right triangle definitions today, so the trig functions will take in an angle in a triangle and give us back a ratio of specific sides of the triangle. So if we give ourselves a nice right triangle here, and that right triangle is at some angle, I'm going to use theta here, no matter how big or small this triangle is, as long as that angle stays the same, the ratio between all of the different sides of that triangle are going to remain constant. So if we make it really small, okay, the sides are small, but the ratio between this length and that length, or the ratio between this length and that length, always stay the same. So we have a relation between angles and different ratios of side lengths, and a relation is what we call a function. So because there are so many sides here, we've got different ratios that we might be caring about. And the 6 ways we can get ratios there are our 6 trigonometric functions. So the first one that we often talk about is the sine function. And the sine function gives us, as talked about here in your notes, the sine function gives us the ratio between the side opposite the angle in question and the hypotenuse of our right triangle. And we'll often abbreviate this as SIN, sine of some angle, outputs the ratio between the opposite side and the hypotenuse of a right triangle containing that angle. Similarly, the cosine function, which we abbreviate COS, but please don't say cos, cosine of an angle, gives us the ratio between the side adjacent the angle up against the side adjacent the angle and the hypotenuse. So that's the opposite and the hypotenuse for sine, the adjacent and the hypotenuse for cosine. Well, we'd also want to talk about the opposite and the adjacent, so our tangent function, abbreviated TAN, of some angle, again, try not to say tan, tangent of theta, will give us the ratio between the opposite side and the adjacent side of our triangle. So for example, if we had a triangle here and given some angle A, if the lengths of this triangle, say, were 5, 12, and 13, then the sine of angle A would be the ratio between the opposite side, the 5, and the hypotenuse. Hypotenuse is always opposite the right angle, so the hypotenuse 13. cosine of A would be the adjacent 12 to 13. Tangent of A would be the opposite of A, 5 over 12. The adjacent. Now we do have to be careful. These are specific to angle A. If we look at angle B here, angle B, well, the sine isn't specific to the triangle. It's specific to the angle in the triangle we're looking at. So sine B, the length opposite B, the side opposite B, is that 12. So it turns into 12 thirteenths. The cosine of angle B, the adjacent side to B is that 5. So 5 over 13. And the tangent of B, opposite over adjacent, so opposite B is the 12 over 5. So we do have to be careful. Which angle are we referencing changes whether we're talking about, in this case, the 5 or the 12 or the 5. Now you might notice some relationships in here, and we'll talk a little bit more about those relationships in a bit. But before we get too far, I do want to talk about our other trigonometric functions, because I said there were 6. And you might be asking yourself, well, we've got, this pairing, we've got this pairing, and we've got that pairing. How could there be 6? Well, if we go on here, the cosecant, we start getting into the fun names, abbreviated CSC, cosecant of our angle theta. Well, it's not that it's a new pair of sides, it's just a new order in the pairing of sides. The cosecant is the hypotenuse in relation to the opposite, or in ratio to the opposite. So it's the same pairing as sine, just in the opposite orientation. Similarly, the secant function, which we generally abbreviate SEC, of our angle, is the hypotenuse over the adjacent. It's the same pairing as cosine, just in the reciprocal orientation. And our last one, tangent. Oops, sorry, not tangent. We have tangent. Cotangent. Abbreviated COT of theta. Well, that's the same as our tangent. Same pairing, just it's reciprocal. And that's where we get these reciprocal identities here, that the cosecant is the same as 1 over the sine. It's the same as the reciprocal of our sine. Secant, the reciprocal of our cosine, and cotangent, the reciprocal of our tangent. So that is 6 relationships, 3 pairings, but each pair has 2 possible orientations. So if we dive into your notes here, we're given a triangle. We're told it's a right triangle because it's got this right angle symbol in it. But you will remember, if you're ever wondering if something's a right triangle, you can always use Pythagorean theorem to check the fact that 3 squared plus 4 squared, does that equal 5 squared? For it to be a right triangle, the Pythagorean theorem has to hold. So is 9 plus 16 equal to 25? Yes, it is. So that is indeed a right triangle. and we're asked for the values of our six trigonometric functions in reference to this angle alpha. It looks like an A, but it's got that little top part, so it's the Greek alpha. So our sine should be the opposite, so the leg opposite is that 4. Hypotenuse has to be opposite the right angle, so 4/5. Cosine, the adjacent, so the one up against the angle, so 3/5. And tangent, opposite over adjacent, so 4/5. And then the other three, we can get the other three by our definitions, but they're also just the reciprocals. So the cosecant is the reciprocal of sine, so it's just automatically the 5/4. Secant is the reciprocal of cosine, so it's automatically just the 5/3. And cotangent's the reciprocal of tangents, so 5/4. And that's really all that the trigonometric functions do. They relate an angle to what your side ratios are. And which side ratio depends on which trig function you're using. More to the point, which trig function you should use depends on which side ratio you want. Now, down here we're asked the same thing. The difference here is we're not given all the sides of the right triangle. We're told, okay, that's side length's 8, that side length's 10. We don't know what the hypotenuse is. Oh no, we need a tool. But we already talked about that tool. We need our nice Pythagorean theorem. Pythagorean theorem will give us the third side of any right triangle. So the first thing we have to do is go off to the side and say, okay, 8 squared plus 10 squared had better equal whatever that other side length is squared. So what, 64 plus 100 is c squared, so 164 is c squared. So c is plus or minus the square root of 164. And I don't want to deal with a 164, that's kind of large. Can we shrink that down at all? Well, it is divisible by 4. That's 4 times, what, 41? So C is equal to plus or minus 2 times the square root of 41. Yes, I want you to do this. I always want you to fully reduce your radicals. If you're not used to doing that or not in practice of doing that, it's a great opportunity to practice doing that. It will make the things that we do easier as we go along. I also do want you to be careful and remember your plus or minus when solving for c squared. Since this is just an everyday triangle, this length can't be negative. So 2 square root of 41, but it will come up, and in not too long, that we will look at negative distances. So we will want that plus and that minus. So be sure you're solving completely and solving with all the skills that you have. Then interpret. In this kind of case, I don't need the negative one, so we're just going to go with the positive one. But okay, once we have that, and most right triangles, frankly, will have radicals in them, will have irrational lengths. The 5, 12, 13, and the 3, 4, 5 right triangle, they're called Pythagorean triples, are fairly rare. So expect there to be radicals in most of your right triangles by default. But again, that doesn't change what our trigonometric functions stand for. Our trigonometric functions are still our ratio of sides, and which ratio depends on which trigonometric function. So sine is still, we're referencing angle A, so it's still opposite over hypotenuse. Now you may look at that and go, wait a minute, aren't we supposed to rationalize our denominators? Shouldn't we clean that up? And you are absolutely correct. You should totally clean that up. 1, I might get rid of that. 2, just right off the bat. And then that's going to be 5 square root of 41 over 41 when nicely rationalized. Do I want you to rationalize your denominators? Yes. Working. So make sure you do that. And just like you're simplifying your radicals, make sure you practice that. Now sometimes later on, we'll get some denominators that have irrational pieces in it that are kind of big and nasty, and we won't necessarily be benefited by rationalizing them, and we won't, and I'll talk about that. But in general, with these little fractions, absolutely rationalize them. So cosine of A is going to be 8 over 2 square root of 41. And again, clean that up and then rationalize it. If you need a review on rationalizing fractions, either go off and find one or let me know and I can throw one out. Tangent opposite over adjacent, so 10 over 8, and we do want to reduce that ratio. Again, we're interested not in the side lengths themselves, but the ratio of the side lengths. So, since the ratio of 10 to 8 is the same as the ratio of 5 to 4, they're the same ratio, and we want the simplest version of that ratio. Now, cosecant. Again, we could go back up and look what cosecant is hypotenuse to opposite, but also remember it's just our reciprocal of sine. So we could take the reciprocal of this and then re-rationalize it, but I'm tempted to just look here. This was 5 over the square root of 41 before we rationalized it, so just take the reciprocal of that version of it. Save you some work. Same thing over here, square root of 41 over 4, since secant is the reciprocal of cosine. And cotangent, reciprocal of tangent, so 4/5. So that might take some practice with dealing with the radicals. If you've dealt with a lot of radicals in your background, you might be like, oh, okay, that's no problem. But if it's been a while, that can be a little bit of a chore. So make sure you build those skills back up. We want those skills. So here we're asked to suppose we have a right triangle ABC. So I'm just going to draw that nice right triangle ABC. See if I can make this smaller. That might help. So triangle ABC. The ABC is just referring to the vertices. So we have A, B, and C. Such that the side A opposite angle A, standard notation, side A opposite angle A, side B opposite angle B, side C opposite angle C. It is standard for angles or vertices to be capital letters and side lengths and sides to be lowercase. We're told here that side C is the hypotenuse, which means this is the right angle. Doesn't look like it in my diagram. That's okay, our diagram doesn't have to be to scale, but it might be a good idea to go, okay, I'm going to redraw this thing a little bit once I'm told that information. And we can put the A and the B anywhere we want, it doesn't matter. C, A, B. And now it might look a little more like we want it to. Didn't have to, but probably nice to do that. Find lengths of the missing sides, given that the cosine of B, the cosine of b is 4/5 and that a is 10. Okay. Well, this is our angle B. We know that the cosine of B had better be the adjacent length, which is A, over hypotenuse, which in this case is C. We're told that the cosine of B, this is just our definition of cosine, adjacent over hypotenuse. I'm actually going to write that first. Adjacent over hypotenuse. That's our definition of what cosine is. In this particular case, our adjacent is labeled A and our hypotenuse is labeled C. We're told the cosine of B is 4/5. We're told the length A is 10. So can we find this side length C? Well, and that's something we should be able to solve. A little property of proportions gives us that 50 is equal to 4C. So 50 over 4 is C, which would reduce to 25 halves. So C is a nice 25 halves. Now, if we want this side length B, we could use a different trig relationship if we wanted to, but once we have two sides of a right triangle, finding the third side is just Pythagorean theorem. So, Pythagorean theorem again, a squared plus b squared equals c squared, as long as a and b are legs and c is the hypotenuse. So that's going to be, what, 10 squared plus b squared equals 25 halves squared. So 100 plus b squared equals 25 squared over 2 squared, so 4. So 400 plus 4b squared equals 25 squared. That's 25 25s. Is that 625? I think it's 625. So 400 plus 4b squared is 625. So 4b squared is 225. So b squared is 225 fourths. So b is plus or minus the square root of 225 fourths. So b is plus or minus, 15 halves? And of course, we'll disregard the negative because it's a raw triangle length. So that took a little bit of manipulating. You wouldn't necessarily have to use this solving methodology. I kind of just did it however I want to. But however you get there to get to a nice 15 halves, do keep in mind that we want to stay in exact values as much as possible. So we don't want to be finding, decimal approximations of square roots and whatnot. So the more you can work by hand, stay away from those calculators, the faster you'll get, the more accurate you'll get, the happier you'll be as we go along. So we can do kind of a lot to manipulate within a right triangle depending on what information we've been given. Oh, special triangles. There are a couple triangles that I want to say like, a couple of triangles that are special. And you might remember when we looked at our circle in terms of angles. Ooh, it's terrible. We looked at pi over 6 and pi over 4 and pi over 3, pi over 2. Again, hopefully you're practicing, filling out the circle in terms of radian measure. And these were equivalent to 30 degrees, 45 degrees, 60 degrees, and of course 90 degrees up there. But we didn't look at pi over 8s. We didn't look at 20 degrees. Why are 30, 45, and 60, pi over 6, pi over 4, and pi over 3, the kind of primary angles we look at? And the reason is because they form these very special, very specific triangles that we know more about than most other triangles because of some of the geometric particulars of these triangles. What do I mean by that? Well, let's look. If we consider a right triangle that has 45 degrees as its other angle, so this is our isosceles right triangle. This triangle is handy because if these angles match, it's an isosceles triangle, that means these side lengths have to match. So instead of one being A and the other being B and us not knowing, we know that they're the same length. And then this other side, C, is going to be the side that's different. And when we talk about the trig functions, again, the trig functions are only about ratios, so we don't need to know, if we want to talk about the trig functions, we don't need to know how long these are. All we need to know is how long they are in ratio to each other. So it can be handy to just choose a side length. And I'm going to choose this side length C to be 1. I know that's a little bit of a different choice than they might have made over here, but it is. But I want to make this choice and just show you where it goes. It'll be equivalent, so don't worry. But what I mean by being able to choose that as 1, if we can find the length A given that C is equal to 1, then we can find that ratio, and that ratio will be true regardless of the size. How can we do that? Well, because these two A's are the same, our Pythagorean theorem only has one variable in it. We know that A squared plus the other A squared has to be the hypotenuse squared, 1 squared. So this is something that we can solve because we don't have an A and a B. We don't have two variables. So A squared is 1/2. So A is plus or minus the square root of 1/2, which of course we're not going to leave like that. Plus or minus, that's the square root of 1 over the square root of 2, which we're going to rationalize. And I know it irritates you, but we want to be rationalizing our things. So a nice square root of 2 over 2. Now I know plus or minus, these are just lengths here, so we're not going to need the plus or minus. But again, we will later, so get in that habit. So if we have a right triangle with 45 degrees on each side, or each vertex, then this ratio of sides is going to be the same no matter what. So if this hypotenuse was, instead of length 1, say it was length 5, then this is going to be 5 times as long. It's going to be 5 times the square root of 2 over 2. And this side length will be 5 times the square root of 2 over 2. If this hypotenuse was a 13, if this length was 13, then this would be 13 square root of 2 over 2 and 13 square root of 2 over 2. And notice that's the same ratio that we have here. It's just they have the square root of 2 on the hypotenuse, and I have the square root of 2 over 2 on the legs. And we'll talk a little bit later about why I prefer this, but it's the same ratio. And one of the reasons that this is handy is now if somebody comes up and says, hey, what is the sine of that 45-degree angle? Well, we know what the sine is. The sine is our opposite side in ratio to our hypotenuse. If we're talking about this 45-degree angle, if we were talking about this 45-degree angle, this root 2 over 2 would be the opposite, but they're the same, so it doesn't matter. So the sine of 45 degrees is the square root of 2 over 2 over 1 for the hypotenuse. That's one of the reasons I like the 1 on the hypotenuse. So it's square root of 2 over 2. What's the cosine of 45 degrees? Well, the adjacent side is still square root of 2 over 2. Over the hypotenuse is still 1, so all over 1. All over 1 goes away. We don't need it. Now, is that the same thing we would get over here? It would be s over square root of 2s. And then the s's would cancel. You'd get 1 over the square root of 2, which you'd rationalize into the square root of 2 over 2 again. So it's the same relationship. I just prefer to do the rationalizing once and have a slightly ickier looking triangle than do that rationalizing every time. And it fits nicer into one of our tools later. Then the tangent of 45 degrees, opposite over adjacent. So square root of 2 over 2 over square root of 2 over 2. That might look ugly, but since they match, that's just a 1. So we can fill a lot of this out. 45 degrees is the same as pi over 4, so we know what the pi over 4 is. It's square root of 2 over 2. Cosine of pi over 4, square root of 2 over 2. Tangent of pi over 4, 1. Reciprocals are cosecant of pi over 4. It's going to be the reciprocal of root 2 over 2, so we could go 2 over the square root of 2 and then rationalize that. That's a little bit irritating. 2 square root of 2 over 2, those cancel and we get the square root of 2. But also just remember where it came from over here, that 1 over square root of 2. It's really the reciprocal of that. So either way, it's a square root of 2. Same for secant, because those were the same. Cotangent, reciprocal of 1 is 1. All from knowing this nice triangle. So one of the reasons we like these 45-degree angles, these pi over 4 multiples of angles, is that we can geometrically determine the trig values for it. Okay, so that's the pi over 4 angles, the 45-degree angles. What about the 30s and the 60s, the pi over 6 and the pi over 3? Well, similarly, we like them because we could make a nice geometric argument for them. So if we look at a pi over 6, pi over 3 right triangle. Again, that's 30 degrees up here, 60 degrees down here. After a while, I'll stop reminding you of that because you'll get so used to it, but for right now, I'm going to remind you. And we still have lengths A, B, and C, and similarly, I'm going to make a slightly different choice than what they did here. I'm going to let this be 1 as opposed to letting this short length be 1s like they did, but you can do it either way. But there are going to be benefits later for that, letting that hypotenuse be 1. Now, we can't use the Pythagorean theorem trick we used before because we don't know that A and B are the same. They're definitely not the same. So we need a different trick. But it's still a fairly simple trick. If we take this triangle and rotate it or flip it over this side to build a big triangle, that big triangle still has pi over 3. If we flip this side over here, or this angle over here, this would still be pi over 6. But remember, this is still 60 degrees. This is still a little 30 degrees. That means together, these make another pi over 3 angle, another 60 degree angle. So this is a 60, 60, 60 angle, or pi over 3, pi over 3, pi over 3 triangle. It's an equilateral triangle. All the angles are the same, so all the side lengths must be the same. That makes this whole side 1, and this whole side 1, because we chose this side to be 1. Well, if that side is 1, and these are just mirrors of each other, this side length A had better be 1/2. Now again, they use S and twice S, and I have 1/2 and twice 1/2. It's the same relationship, just with some different choices made. But since all we care about is the ratios, that's okay. Sorry. So what we've got so far is a right triangle where if this length is 1, that length is 1/2. We'd still like to know the other side. But now that we have 2 lengths, we don't need our geometry, our trig anymore. We can just use Pythagorean theorem again. Pythagorean theorem is going to be our friend throughout this course. So 1/2 squared plus b squared equals our c squared. Do make sure the hypotenuse is always what the sum is equal to. 1/2 squared is 1/4 plus b squared equals 1. So b squared equals 3/4. So b equals plus or minus the square root of 3/4, or plus or minus the square root of 3 over 2. And that's that same square root of 3. I just don't have the halves because I made, again, different choices. And you'll see those choices pay off as we go on, I think. Now again, for this plane triangle length, we're going to use the positive version, but I hope I'm making it clear that you want to be in the habit of that plus or minus. It's going to bite you later if you don't. So if we consider this pi over 3 angle down here, we can say what the sine of pi over 3, what the cosine of pi over 3, and what the tangent of pi over 3 are as a result of this geometric argument. And if you use these, you'll get the same ratios. Things will just cancel differently. You'll be doing the rationalizing work here as opposed to doing it here, and that's okay. So what is the sine of pi over 3? Well, the opposite in ratio to the hypotenuse. So square root of 3 over 2 over 1, which is just the square root of 3 over 2. Cosine of pi over 3, 1/2, the adjacent side, 1/2 over 1, so 1/2. Tangent of pi over 3, well, opposite over adjacent, so the square root of 3 over 2 over 1/2. Clean that up by multiplying by 2, and we'll get the square root of 3 over 1, or just the square root of 3. And you can do all their reciprocals. Make sure you rationalize them to fill out your table. Similarly, the sine of pi over 6, cosine pi over 6, tangent pi over 6. Same triangle. As long as we know this triangle, we will know those trig values for our, what we call our standard angles. Our pi over 6s, our pi over 3s, our pi over 4s, and their multiples. Once we get there. It'll be another day or two. But just for completeness, sine of pi over 6, the pi over 6 is up here. So pi over 6, its opposite is the 1/2, its hypotenuse is the 1, so 1/2. Cosine, the adjacent, is now the square root of 3 over 2 over 1. And tangent is opposite over hypotenuse, so 1/2 over the square root of 3 over 2, which is a little bit uglier, but again, multiply by 2 to clear out that fraction, 1 over square root of 3, which you'll then rationalize, multiply by the square root of 3, multiply by the square root of 3, and you'll get the square root of 3 over 3. So tangent of pi over 6, square root of 3 over 3. Cosine of pi over 6, square root of 3 over 2. Sine of pi over 6, 1/2. And you can fill out their reciprocals. So we're going to get a lot of traction out of knowing these two triangles. And you'll hear me refer to them quite often. You'll see them referred to quite often. Because they allow us to know a set of trigonometric values simply by the geometry. And we're going to find that to be a really helpful tool. So what do we got here? Starting to get a little bit long, but that's okay. I try to keep these under an hour, but we'll see how we do. So what do we got here? A surveyor measures an angle of elevation. Elevation is always up from the horizontal. So surveyor declination is down from horizontal. So an angle of elevation from the position to the top of the mountain to be 45 degrees. So some mountain. And they measure this angle of elevation to be 45 degrees. Now that could either be a coincidence or because they went and set up their equipment to make that happen. It's usually the way it is. Walking an additional kilometer away from, so go an additional kilometer away, 1 kilometer from the mountain. The angle of elevation is now 28 degrees. So 28 degrees. I'm going to draw that better. This is a good tip, by the way. Always draw diagrams. Always, 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 always. But never consider your diagrams sacred. If you draw a diagram and you're like, that diagram's not doing what I want it to do, then redraw it. a good diagram will save you a lot of time and worry. So that's 45 degrees, and then they go a kilometer away, and it's now 28 degrees. That looks a little bit more reasonable to me. And this is 1 kilometer. And approximate the height of the mountain. So we want to approximate this vertical height. Okay. Well, this diagram contains actually a lot of triangles. There's this little 45, 45 right triangle. That's this one. There's this big triangle, the 28 degrees. And what would the other angle have to be? It'd have to be, what, 62 degrees. 90. There's also a little triangle in between those where that's our 28 degrees and this is, what, 135 degrees. The trouble is, this isn't a right triangle, this little triangle here. It's not a right triangle, so we can't really do anything with non-right triangles yet. At some point we will be able to, but not right now. So given what we know, we want to find this height, and all we know is that this length is 1 kilometer longer than that length. However long this is, x, that longer triangle is 1 kilometer longer. Okay, so what are we going to do with that? Well, when in doubt, just start writing down things that we know. We know that the sine of 45 degrees is equal to that h, well, not sine. Why did I pick sine? I don't want sine. How do I know which trig function I want, by the way? We understand, or we have, the opposite length we're talking about here and the adjacent length. I don't know the hypotenuse. I'm not asked for the hypotenuse, so I'm going to stay a little bit away from the hypotenuse for a while. We have arguments about the opposite and the adjacent, and tangent talks about opposites and adjacents. So let's talk about tangent. The tangent of 45 degrees we know is equal to h over x. But we also know from our work above that the tangent of 45 degrees is equal to, it might seem strange that we know that, but we just worked that out. The tangent of 45 degrees, or pi over 4 angle, is 1. So that tangent of 45 is 1 equals h over x. So x had better be the same as h. And that should have been fairly clear. I mean, this is 45, 45, so this is an isosceles triangle, so that x and h had better be the same. Well, that's lucky, because that means this is h, that's h, that's h, and that's h plus 1. Since all our x's are now h's. Okay, let's go over to this triangle now that we know that. Again, we've got arguments about opposites and adjacents, so I'm going to stick with tangent. That the tangent of 28 degrees, now I don't know what the tangent of 28 degrees is off the top of my head, it's not one of our standard angles, but we can use a calculator to find that. And we know it has to be equal to this ratio, the ratio of h over h plus 1. And this is something we can solve for h. Multiply both sides by h plus 1, tangent of 28 degrees times h plus 1 equals h. I'm going to distribute, remember this tangent of 28 degrees, you could type it into a calculator and get a number. No question that you can do that. But that number is going to be some big ugly number. And I don't want to carry around some big ugly number through this problem, so I'm just going to leave tangent of 28 degrees as it is and manipulate it like it's just a number, because that's all it is. So I'm going to distribute it into here. Tangent of 28 degrees times h plus the tangent of 28 degrees times 1, just tangent 28 degrees, equals h. Still trying to solve for h, so I'm going to subtract the tangent of 28 degrees times h from both sides. Subtract, I'm going to write h tangent of 28 degrees. It's nice to have the variables out in front so it doesn't look like it's part of the argument for the tangent. Or you can use parentheses, whatever makes you happy. So we get the tangent of 28 degrees equals h minus h times the tangent of 28 degrees. Still trying to solve for h, so let's factor it out. 1 minus the tangent of 28 degrees equals the tangent of 28 degrees. And then divide that off. And we'll have h equals the tangent of 28 degrees, whatever that is, it's some number, over 1 minus the tangent of 28 degrees. Now you might have been more comfortable way back here turning this into a number and carrying that number through the problem. But I want to kind of encourage you to think about your solving in this way. It really is very handy. One, it stops us from making errors in our decimal approximations. It keeps our approximation error as little as possible. And frankly, once you're comfortable manipulating things this way, it makes a lot of things quite a bit easier. But at some point, it would probably be nice to ask a computer or a calculator what that value is, so we can say, and it would be in kilometers, because this one is in kilometers, all these lengths are in kilometers, and figure out what that height is, and hopefully you'll do that and have that actual height in your notes, and write the mountain is whatever kilometers high. But I'm going to try to convince you as the course goes on that working in this exact way is handy. We'll see how that goes. See if I can convince you. Ooh, running out of time here. How many more of these do I have? Ooh, I got a lot. Ooh, cofunctions. Okay, we'll meld the rest of this with the part 2 video. I want to do at least one of these examples to finish us up, but then we'll do the cofunction thing on the other video. So a surveyor standing 30 feet from the base of a large tree measures the angle of elevation to the top of the tree as 57 degrees. What is the height of the tree? You'll see a lot of these height type problems or these surveying type problems. They just give us a nice visual reference to what we're doing. So we want that height. Again, we're asked about the opposite side, we're given the adjacent side. Which of our trig functions deal with opposites and adjacents? Well, tangent and cotangent both do, but tangent is our nice primary one, so we're going to grab tangent for this problem. Tangent of 57 degrees, that's got to be h over 30, because it's the opposite over the adjacent. Multiply both sides by 30. 30 times the tangent of 57 degrees equals h. And technically, that's a nice answer. Again, keep in mind what the tangent is supposed to be doing. Tangent is supposed to be giving us a ratio that fits this model. So it's taking that 30 feet and using the ratio of that kind of triangle to figure out what you've got to do to the 30 to get what that height is going to be. So that product, 30 feet times a ratio, is going to be some number of feet. And if you wanted to be exact, and there are, well, particularly you engineers in there often want to be very, very, very exact, the tree is 30 tangent 57 degrees feet tall is a perfectly reasonable answer. You want to find the decimal approximation so you can get a feel for it. It is handy to kind of be able to say, like, you know, if you worked this out and got 12, there's no way it's 12. So it's nice to get an answer to kind of go, oh wait, that doesn't make any sense, or oh, that's a reasonable amount, to kind of give yourself a check, because it's hard to visualize 30 tangent 57 degrees. So getting a decimal approximation is nice, but we don't need it. And again, I'm going to push you on that. Suppose you're constructing a quilt using 30, 60, 90 triangles. Good triangles to use for a quilt. The side opposite the 30 is 7 centimeters, so that's our 7 centimeters down there. Our 7 centimeters. And we want to know the perimeter, so we want to find the other pieces. Okay, well, we could do a bunch of the stuff that we were doing before, but if you remember our triangle from before, that was our 30, 60. Of course, we did it as pi over 6 and pi over 3, but it's the same triangle. And we determined if this was 1, that was 1/2, and this was the square root of 3 over 2. I said knowing these triangles is going to be super handy. Here's one of the points where it's super handy. So we know those ratios have to be fixed. So if this side length is 7, as it is in our problem, then that 7 is half of whatever this is. So this has to be 14. Does that seem reasonable? This length is always half the hypotenuse. So if this length is 7, that hypotenuse has to be 14. You can think of this square root of 3 over 2 as the square root of 3, I want that to be the black, as the square root of 3 multiplied by 1/2. So whatever that half length is, multiplied by the square root of 3, and you get the square root of 3 times that 1/2 length. So is it really just the square root of 3 times 7? Absolutely. And that's all it takes. That side length is 14, that side length is 7 times the square root of 3. So 14, 14 plus 7 plus 7 square root of 3, or 21 plus 7 square root of 3 centimeters. You want to come up with a decimal approximation for that. Perfectly reasonable thing to do. I think it would be around 12-ish for 7 times the square root of 3. So 33-ish centimeters with a decimal approximation. Don't quote me on that. I'm trying to do square root of 3. I think it's a little more than that, actually. Doesn't matter. See, and I could grab my computer and ask it to tell me what it is, but I like to make the point that it's just easier once you get used to it to deal with these exact values. You need 21 plus 7 square root of 3 centimeters per triangle. Or, I guess, what's the perimeter of this piece of fabric? The perimeter is 21 plus 7 square root of 3 centimeters. And if you knew you needed 128 of these triangles to make your quilt, multiply that by 128, then approximate, and you'll get a more accurate answer. Why do you need to be that accurate about thread? I don't know. If you're manufacturing these things on an industrial scale, it could make a big difference, depending on what you're doing and why you're doing it. Okay, have fun with those. We'll talk about the rest of these notes and the other notes in the next video. And have a wonderful day.